it goes. All right, so we have the Paulie exclusion principle. It says that no two electrons can share the same set of quantum numbers. We have to be able to know which one's allowed, which one's not. It's just a simple yes or no, up or down, but you got to remember the order. You know, n equals 1, 2, 3, 4, whatever. L is 0 to n minus 1, and then we have m sub l is minus l to plus l, including 0. And we have SPDFF, speed FFFFF. And then we have, of course, the electrons can be up or down, plus or minus a half. Alright, so now we have to have some sort of notation to be able to say something about the electronic configurations and what they are. So the first kind that I'm going to go over is something called the box configuration. Alright, box configuration. These are notations to describe or to illustrate where electrons are in an atom or a molecule. Okay, and so the way it works is like this. We have these boxes, and I'm going to just draw out some boxes. All right, and the way this is going to work is we're going to have, like, this is going to be the box itself is going to be the subshell, or your L. Okay, all right, and this is going to be the level. So this is a 1s, this is a 2s, and this is a 2p. And the number here, this is going to be your primary. Okay, this is going to be your primary. And so when we fill up electronic levels, and this is your primary is your 2, and your subshell, this is your L, so you got S and P so far. And so within these boxes, we're going to put electrons. Okay? And so the individual boxes is going to be essentially m sub l, although we're not going to designate them as being -1, 0, or +1, but essentially they are your m sub l, or your orbitals. Okay, and S only has one orbital, which is why there's only one box for your S sublevel. A P sublevel has 3 orbitals, and that's why you have 3 boxes, because each box represents an orbital. All right, and so if we have something like, now here's the rule. Here's the rules. We're going to fill one subshell at a time. In other words, we're going to fill the S before we move on to the next S. We're going to fill that S before we move on to the P. We're going to fill one subshell at a time. And then 2, we're going to fill one electron at a time per box. Per box orbital. Okay? And we're going to pair electrons only after all boxes in sublevel are full. All boxes in sublevel are full. So this is the general plan here, okay? So we're going to fill one subshell at a time, a subshell being an S or a P or a D or an F. We're going to fill each box one electron at a time, and when we pair electrons, we're going to pair arrow up, arrow down, arrow up, arrow down, up, down, when we do pair them. Okay? Alright, so that's the rules. So I'm going to pick one arbitrarily. I'm going to pick a carbon atom. Alright, now, how many electrons does a carbon atom have? And we look at the periodic table and we see that this is element 6, and so therefore it has how many protons? It has 6 protons, and therefore since it's neutral it has 6 electrons. It is element 6, right? So I check my periodic table and I find carbon. And where is carbon? Carbon is element number 6. It's the number over the top of it, okay? Being element number 6 also means it has 6 protons, which means it has 6 electrons. Since the overall charge of a neutral anything means it has a charge of 0. 6 minus 6 is 0. Okay, so we have 6 electrons. What's the rule here? We're going to fill one subshell at a time. And we're going to put 1 electron per box until we have a pair of electrons. So I go, here we go. So I have 6 electrons. So here's 1. There's 2. I'm going to pair opposite. I filled the first S subshell, 1s. 1 being n equals 1, 2 electrons in the first L, which is L equals 0. Okay? Now we go on to the second one. I have 4 more electrons left. So I go 1, 2. My S can only hold, my subshell S can only hold 2 electrons. My S subshell only has 1 orbital. Each orbital only holds 2 electrons, maximum. So I filled up my 1s, I filled up my 2s. Now I have 2 more electrons left. Now, what's the rule here? We're going to fill them up one at a time per box. And so I go 1 more electron, that makes 5. 2 more electrons, that makes 6. So this is the box configuration for carbon atom. Carbon is, if you look on the periodic table, it says 6, 12.011. We already know the 12.011. That's, grams per mole. That's a weighted isotopic average. And that is number of protons, number of electrons for neutral atom. Okay? All right. Let's do another one. Okay, so let's say that we're going to do chlorine. All right, now there's my 1s. Here's my 2s. More on the order on this in a little bit. There's my 3s. I mean 2p, I'm sorry, excuse me. 3s is next up. And here is my 3p. Okay. So how many electrons does chlorine have? So step 1, number of electrons for chlorine. And we look on our periodic table and we see chlorine is element number 17. And we see 17 electrons total. Alright, that's going to be important later when we talk about valence electrons and such. But right now we're just looking at the total number of electrons. We have 17. 17 electrons. Okay, so we need to count them up. And so we go, alright, so let's do this. So we say, here's 2 electrons. Arrow up, arrow down. Here's another 2. That makes 4 altogether. Arrow up, arrow down. We go to the 2p's. Now remember what I said. We're going to fill one box at a time, one sublevel at a time. And when we pair them up, we're going to pair them up, two electrons, arrow up, arrow down. All right, now watch this. Now watch what I'm doing. Okay, so we're going to go arrow up, arrow up, arrow up. That's 3, right? Okay, now I have room for 3 more, but notice what I did. I did them one at a time per box. Now I'm going to come back and fill them up because I've got 17 electrons to go. I've only put down 7 so far. So here is 8, 9, and 10. Do not jump ahead and pair them up. Okay? Don't pair them. Don't go two. Don't do this. Don't do this, this, this. You see what I'm saying? Go 1, 2, 3, and come back. Okay? Get in the habit of doing that. Now, technically, it wouldn't be incorrect if you did that, because if you know ahead, then you would know you already filled it up. Okay, now we're finished with the 2Ps. And how many have we put down? We put down 10 so far. We put down 10 so far. So what do I have left? 7 more to go, right? And so let's do 2 more for the 3s. Arrow up, arrow down. We just finished. Remember what I'm doing. Sublevel at a time, 1 arrow at a time, 1 per block. Okay, now I have 5 left. Everybody agree I got 5 left? All right, so I go, remember, 1 at a time per block. 1, 2, 3. Okay, that's 3. Now I can come back and go 4, 5. All right, now I have 17 electrons. I have them in order, okay? And the last one I filled was the last highest energy level, okay? One way of looking at this is we're filling from the bottom energy to the highest energy, bottom to top. We're just kind of pouring in the electrons and filling them up. But look what happened here. When I had choices between boxes to do, I went arrow up, arrow up, arrow up. Then I came back, went arrow down, arrow down. You see that? So this is the this is the box configuration for chlorine. Okay, this is the box configuration for chlorine. Now, most of the time, I want you to focus on something here. You see this 3, and you see a 3 there, right? Okay. The highest energy outermost these are the outermost. So these are the outer electrons. They're on the outside because we're filling up shell, 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 shell. We're filling up shells. That's kind of like that whole Bohr atom thing, you know, we're filling up shells. We're sort of filling up shells there. So as we go, so the last electrons we put out there are actually on the outside of the atom. They're on the outside, and we call these valence electrons. They're the outermost electrons, okay? They're called the valence electrons. More on that in a second, okay? All right, so now let's do one more, and then we'll move on to the next thing, which is valence electrons, okay? And we'll show you how to get them. But I just want to point out that the outermost electrons are where all the interesting things are happening. So let's do one more. Let's do aluminum. All right, so I'm going to do aluminum. So I put down Al, and we're going to go ahead and just put down the boxes. By the way, you're always given the boxes. You just have to decide which ones to use. All right, so we have aluminum. And I look on the periodic table, and I see that aluminum has 13 electrons, and it's on the 3rd row, so I need another row of these guys, 3s. Okay, and it has how many electrons? Aluminum has 13 electrons. So can we fill this out? And so how would we do this? We would literally count off 13 electrons, and I'm going to show you a shortcut to all this in just a second, but we would literally go up, down, up, down, up, 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 down, 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 up, down, and then we would go 3p1. There it is. There's your box configuration for aluminum. Okay, and it should be 13 electrons up there, so we go, let's see, that's 2, 4, plus another 6 is 10, plus another 3 makes 13, so sure enough, there's 13 electrons. Okay, now, let's take a look at our periodic table as we did this. Let me draw a periodic table, and we'll draw one real quick here. Okay, any questions on this so far? If you have these boxes in order, you should be able to just fill them up in order. All right, now, let me show you something here. I'm going to draw a periodic table. Here we go. Here is a periodic table. All right, that's a sketched out kind of rough periodic table, all right? And if you look at the periodic table over here, you will notice that that we have hydrogen, and then we have, what's down here? We have lithium, beryllium. And if you go all the way across over here, we have helium. And then, of course, it's like boron, carbon, nitrogen, oxygen, fluorine, neon as we go across, right? All right, now, it turns out that the periodic table is actually arranged according to electronic properties. This section over here, which is too wide, this is actually too wide, this is actually called the S block. This section over here, if you look at a periodic table, you will see that this is actually 6 wide from here to there. And guess what? What has 6 electrons maximum? Your P's. And if you look at this valley in here, you will see that this is 10 elements wide, and what has 10 maximum electrons? Your D elements. And if you look down at the very bottom at these guys on your periodic table, you will notice that these are also 14 wide. This is actually 14 wide. And these are actually your F elements. The periodic table is actually arranged according to electronic configurations. It's actually arranged according to the periodic table is arranged according to electronic configurations. Now, if you look, these go rows, 3, 4, 5, 6. And these are, of course, the periods. You have row 1, row 2, row 3, row 4, row 5, row 6, row 7. And it turns out the period equals the n number for the S's and P's. The row actually is the primary quantum number. The periodic table is arranged in rows by the periodic table is arranged by rows according to the primary quantum number. If you're in row 1, your primary quantum number is 1. If you're in row 2, your primary quantum number is 2. It actually goes back to this whole mess right here. Remember that? This is astonishing. If you really think about it, the arrangement of the periodic table has everything to do with the electronic levels, which are arranged just like this within an atom. It literally goes by rows. Now, it is n minus 1 is the n number. Pardon me. It's row minus 1 is for the D's, by the way. Okay, that's your primary. Now, because of this, the way these things work is every time you finish a period, you finish a shell. Every time you finish a period, you finish a shell. So where are our full shells? Our full shells is at our noble gases. So all our noble gases equals full shell. Okay? All your noble gases equal full shells. Where are our noble gases? All the way on the right-hand side of the periodic table. All right? So what's important is what's on the outside of the atoms. Okay, what's on the outside of the atoms is the things that are actually going to do the bonding. All the exciting stuff happens on the outside of the atoms. All right, everybody with me so far? Everything on the outside is where everything happens. So when you finish a shell, you start a new shell. And if you start a new shell, and say you finish a shell and you start a new shell, this is on the inside. And these guys are on the outside. All right? So if you finish a row, when you start a new row, you're starting a new shell, and they're on the outside. And so everything prior to that is on the inside. Now, on the outside is where all the exciting stuff happens. If you think about it, if you have an atom next to an atom, where are they touching? They're touching on the outside. Okay, and that's where all the bonding and so forth. That's why the outside is the part that really matters. And so if we go back to this guy right here, what's on the outside? It's these guys. Where did we finish the shell? This is where we finished the shell. Row 2. 2p, row 2. Remember what I said, the n number is the same as the row number. So when we finished row 2, we went on to row 3, which is where the s's were and where the p's were. And so we finished the shell there. So what's on the outside? It's the highest n number. So these are the highest n number, which means they're on the outside, which means they're valence electrons. Okay, valence electrons are on the outside. Okay, they're on the outside. All right, now what we have to be able to do is we have to be able to look at a periodic table and say how many valence electrons does this element have. And it's actually easier than it sounds. Let me pull up a periodic table for you. Okay, let me go ahead and do that. So I'm going to go ahead and open up my browser, and I'm going to find a periodic table. I'm going to copy it and I'm going to paste it because it's a lot easier if I can paste and go. Alright, so we're going to do a periodic table here, and this one looks as good as any. So what I'm going to do is I'm going to save the image. Let's see, we're going to copy the image and hopefully it'll let me paste it. Alright, so let's go ahead and paste this guy, and we'll show you something here. Alright, let's see, Control V, and it did let me do it. Okay, that's good. So let's go ahead and see if it'll let me there we go. That's what we're talking about. Now we're cooking with gas. Alright, and so bear with me for a second here. Okay, so we have this periodic table in front of us. Everybody see periodic table? Good. Okay, and so I'm gonna, let's see, let me move this over just a hair, and I'm gonna put the let me move everybody down. Let me move y'all down a little bit. Come on, there we go. All right, so I'm gonna put the row number up here. Here's row here's row number 1, row number 2, 3, 4, 5, and so forth. Okay, here's the row numbers, and that's the period number. Everybody see that? Okay, so we have a row number. Now helium, we're going to move over here. Let's see, I don't think it'll let me, but we're going to move helium all the way over here. So helium, for our purposes, belongs next to hydrogen. Okay. All right, it's kind of hard for me to draw in the picture. It won't let me do that. Or maybe it will. I don't know. Let's see if it'll let me do that. Oh, yes. There we go. Helium belongs there. All right, for our purposes. Now, this section in here is the what? This is the S block. This is the D block. And this is the P block. Everybody with me? Okay, and so the P block is all of these guys in here. D block is all of these guys in here. And the S block is all in here. All right. Now, these actually have numbers, the groups, and so this is group 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and this would be 13, 14, 15, 16, 17, 18. Okay, if you look on your periodic table, it's 18 columns across. All right, but a more common designation is this is called 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. Okay, old designation, but still used. And it turns out that these numbers here is the same as the valence electrons. Okay, so everybody here in this whole column has one valence electron. Everybody in this entire column here, all the way up, everybody has 7 valence electrons. Y'all see that? Everybody has 7. I want to emphasize that. So everybody in group 8A, everybody here has 8 valence electrons. Okay? Everybody. Now, valence electrons is not total electrons. Okay, take a look at chlorine, for instance. Let's take a look at chlorine. How many valence electrons does chlorine have? It has 7 valence electrons. But how many total electrons does it have? It says 17 total, right? Chlorine has 17 electrons. Everybody see that? Chlorine has 17 electrons total. But the electrons that count for us are the ones that are on the outside. And so chlorine has 7 valence electrons. It has 7 electrons on the outside of the element. How many valence electrons does, say, silicon have? How many valence electrons does this one have? It has 4. How many valence electrons does calcium have? It has 2. It doesn't matter that it has 20 electrons total for calcium. What matters is how many electrons does it have on the outside. Because where's the outside? The outside for calcium is the previous finished shell, which is what? Argon. Okay? Previous row is the previous finished shell. Everybody with me so far? Okay? Stop me if I'm not making any sense here, because this is so important. Okay, so if I want to know the number of valence electrons, I just look at the periodic chart and I just count. It goes 1, it goes 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Okay, now what about these guys in the middle? You're going to love this. Don't worry about it. All right, valence electrons for your transition elements depends on who you ask and what you're doing for the transition elements. So strictly speaking, if you go by outermost elements, outermost electrons, it would be 2 for all of them, because the last one that would be filled up would be the 3, that would be the 4s or the 5s or the 6s, and those would be the highest until you get over to the p's. Okay, strictly speaking, there would be 2 valence electrons for all your transition elements, but that's not the case. Okay, it could be like iron. It can have 2 valence electrons. It can have 5 valence electrons considered. It can be considered to have 3 valence. It just depends. It just depends, okay? So what I will tell you is, for the middle elements, as far as number of valence electrons go, don't worry about them. Don't worry about these, all right, as far as valence electrons, okay? So all we're going to care about are our s elements and our p elements as far as valence electrons go. All right, now, hopefully everybody's got a periodic table in front of them, so I don't have to go back and forth to this. Now, let's go back to chlorine again. All right, and except now you want to do the box configuration. We're going back to the box config again, except this time you are presented with 2 boxes. This is what you're presented with. And you say to yourself, well, where do I put all these electrons? Because chlorine has 17 electrons, right? Where do I put all these 17 electrons? Because you said, Mr. Pierce, you said, fill them in 1 box at a time, maximum 2 electrons per box, right? I know what you're saying. But look, these, when we do box configurations, often it's valence electrons. Often it's just valence electrons, because that's what we care about. So how many valence electrons does chlorine have? And you look at chlorine and you say, well, what group is it? And you say, well, chlorine's in group 7A, therefore 7 valence electrons. All right, and so the rules still apply. So I go 1, 2, 3, 4, 5, 6, 7. Ta-da! You see how that works? You have the valence electrons in front of you. You know what you need to do. All right, you just put them in there. Now let's say that someone was being particularly sneaky and puts up, say, and this happens. I've seen this. 2s, 2p, 3s, 3p. Let's say this was put up for you. What are we missing out of this? Ooh, what are we missing over here? And you realize we're missing the 1s, but they're still there. You have to take that 17 and subtract off the 2 that you're missing off your boxes, because someone decided that you don't need the 1s, because the 1s is always filled up, right? Unless you're talking hydrogen, helium, it's always filled up, and so it's missing. So you actually have to put in 15 electrons, and so you're back to 2, 4, so forth. And so once again we're back to 15 electrons, and so we go 2, here's another 6, that makes 8, there's my 10, and there's 1, 2, 3, 4, 5. Okay, do you see what happened here? And so once again, we're still there, aren't we? Yeah, we're still there. This is the outermost electrons. We still have 7 valence electrons here. Okay? But you have to be careful about this sort of thing right there. If when we get into molecular orbital theory, this happens all the time. The bottom most energy levels are left off in these graphs. And so this is an attention to detail sort of thing. You got to look at it and say, wait a minute now, the 1s is always there. Okay, it's always there. All right, now the s's, the d's start with. Now remember what I said. He said, the s's and the p's, the n number is equal to the row number, and the d's, I said the n number is the row minus 1. Okay, and so what that means is that in fact it's going to fill in this order. It's going to go 1s, it's going to go 2s, it's going to go 2p, it's going to be 3s, and it's going to go 3p, and then it's going to go 4s, and then when you hit that fourth row, it's going to go 3d. So it's going to go like this in a very cartoonish sort of way. 1, 2, 3, 4, and that's 3d, 4d, 5d, even though this is 4s, and that would be 4p straight on across. All right, if you look at your periodic table, fourth row, look at your periodic table, you see fourth row, you see 4s, the 4s's. Well, right over it would be 3d. Okay, so if we were to do, let's say iron, then we could start with, we finished with row 3. Where's iron? Iron's on the fourth row, right? Everybody agree it's in the fourth period. So we could actually say 4s for that first box, but then we're going to jump right across into 3d, and then we would go back to, remember, row number is the same as the n number for your s's and p's, and your d's is row number minus 1. So it actually would go like that. Okay, and so where's iron? Iron is the 1, 2, 3, 4, 5, sixth element across on your d's. So iron is right there, and that's 6 across, which means 6 electrons. Has 6 more electrons. So you would go, and the d's, how many orbitals do you have for your d's? You have 5, right? And how many for your s's? You have 3. See the orbitals? You have 1 orbital for s, 2 electrons. You have 3 orbitals. You have 3 orbitals for your p, and so you have 6 total electrons in your p's, and your d's you have a 10 maximum with 5 orbitals. And so you would say for iron, since it's a 6th element across on your d's, you would go 1, 2, and you'd go 1, 2, 3, 4, 5, 6. And there would be your configuration for iron. You got 6 elements across on your D. And remember, we're filling them in one box at a time. Iron is your 6th one across, right? You got scandium, titanium, vanadium, chromium, manganese, iron. So 1, 2, 3, 4, 5, 6. 6 cross on the iron. Do you see that? Basically, you got to be able to count. So 1, 2, 3, 4, 5. We fill them up. We double back up. Okay. How many valence electrons do you have? Well, it depends. If you go by the highest n number, you have 2. Because 4 is higher than 3, even though you filled up the 3 second. 3 is actually still technically lower, because 3 is less than 4. All right, now, so if we were to do this for these D elements, we would predict that this is what we'd get for iron. All right, now let me erase this real quick here. Let me erase this. I'm going to leave this 4s up here, all right, because it's convenient for me to do that. All right, let me show you something here. This is going to be called, now just bear with me here. There's a method to the madness. All right, here we go. So exceptions. There are two important exceptions on how we fill these things up. Now, remember what I said. We fill sublevels from the first one to the second one, right? We'd fill up our 4s, and we fill our 3d, then we fill our 4b, or we fill in our 1s, and then we fill in our 2s and our 2p and our 3s and our 3p, right? We fill, and then we fill them, left to right with the arrows, and then we match up the arrows, right, up and down. With me so far? Yeah. Okay. So if I was to do chromium, let's do chromium. All right, where is chromium? Chromium is 1, 2, 3, 4. It is 4 across. Okay, we're just going to say it's the fourth D. All right, which means there's 4 electrons. And if we were to do the box configuration for chromium, we would say arrow up, arrow down for those first 2 electrons. And we would say 1, 2, 3, 4 for chromium. Chromium is your 4th element across in your D sub shell, right? Everybody with me, right? All right. And being a good student, you would say, well, look, I filled up my 4s first, and I took those 4 electrons and I put them into boxes just like you said. And we go and do an experiment and we find out this is not the electronic configuration for chromium. If we actually physically go do an experiment, everything needs an experiment. And if you go and do an experiment, you will find that this is the predicted, this is what you predict. And here is, I'm going to draw this down here because you need to see both of them next to each other. This is the actual. The 4s electron is promoted to an empty 3d spot. So you actually have 1 electron in the 4s instead of 2 of them, and you have 5 electrons in the 3d. And this is a half filled D. This is a half filled D. And according to some theories, a half filled shell is more stable than a not full shell, not half filled shell. In other words, half filled is better than being 4. So you actually have a lower energy configuration by bumping that one from the 4s into the 3d, so that you end up with a half filled shell. So chromium is exception number 1. All right, now I'm about out of time here, and I'm going to show you exception number 2. There's 2 important ones. Chromium is the first one, and it's because half-filled D shells are more stable. Actually, that's not the case, but that's what we're going to say. All right? Here's your second exception. We are going to have to continue on Monday, but here's your second exception. Copper is your second exception. Chromium being your first, which we just did. Now copper is a 3D element as well. And we would expect it is the ninth one across. So we go 1, 2, 3, 4, 5, 6, 7, 8, and it's the 9th element across on your D. So we would expect that it would look like this, with 1 unpaired at the end. You got 9 electrons. It's the ninth D element. You would expect 9 electrons in those boxes, right? So what actually happens is it's very similar with chromium. One of those electrons gets promoted. Guess what? Right over to there. And so now we have This is actual. And so this is a full D, which is more stable than a not full D. Just like chromium is a full half D, copper is a full D. Y'all see that? These are your two exceptions. They are two very important. These are super important. Super important. Okay, these are your two exceptions. You have chromium, half-filled D, copper, full D. Both of them are made by promoting that 4s into your 3D, from your 4s to your 3D, to either make a half-filled shell or a full-filled shell. All right, and that's when you're half-filled or full-filled, at least for fourth period elements, it's more stable that way. All right, two important exceptions. All right, I'm out of time. I really wished I could have finished today, but I'm not going to be able to finish today. So what we